Good morning, Carl. Yeah. Yeah, no, good morning. Okay. So last time we talked about the Miller approximation, and we said that in the context of the ideal amplifier, where the 2 points 1 and 2 satisfy always a constant gain, as we see here in this example, we can borrow this for purposes of our common source or common emitter amplifier in order to break the capacitance that joins the input. احنا عندنا هيدا VN هون على ال end of the RSig and the هيدي هي فعليا ال output node. So we want to remove the capacitance that is joining the input to the output, break it into two capacitors, one at the input side and another one at the output side. So we remove this and we replace it by two capacitors as we saw last time. And because the gain, we have derived the transfer function, and the T of S, which is T of J omega, is really function of CGD at the different frequencies. We really do not know, yani function of ZGD. We do not have a constant gain. The gain is going to change as function of the frequency and CGD. So we are going, therefore, to fix the omega. We will find the gain at the midband or the low frequency gain without capacitors. Okay, and we will use that in order to divide or split the capacitor into two capacitors, one on the input side at node G and one at the output side between node VO and ground. This is what we spoke about last time, and I'm sorry the session was not recorded, that's why I'm repeating this. هلا what happens here is now when we apply this approximation, we know mid-band gain minus GMRL prime. So CGD will be multiplied into 1 minus K here, and it will be multiplied into 1 minus 1 over K on this side. And we said last time, this means that I will have a total input capacitance Cn, and I will have a total output capacitance اللي هو جمع C load and CGD into 1 minus 1 over K C out. Now, each one of these input circuit and output circuit, if we want to call this facilitates for me to calculate Vn over Vsig prime. Okay, and this facilitates for me to calculate VO over Vn, and their product I can find which is Vn is VGS in this case, okay? And the product will allow me to find the overall gain. My target is to find VO over VGS, so A of S is VO over VGS. Okay, so the mid-band اتفقنا هو K from the mid-band. This is step number 1. So the first step, if we want to look at it this way, the first step, therefore, is we find the mid-band gain, and then the second step is we build those capacitors. This is CGD into 1 minus K. The third step, once I have this, I can find Vn over Vsig prime, and I can find VO over Vn, where Vn is my VGS, and in the fourth step I can find either directly solve for A of S as VO over Vsig prime, or find, so this is for B, this is option B, this is option A, find the 3 dB frequency, okay, and set A of S to be equal, so the 3 dB frequency is omega h, is equal to minus GMRL prime, because this is the low frequency gain over 1 plus S over omega h. So يا إما بنطلعها as a full expression with the different poles that we have, or we find the 3 dB frequency and find it in this form. Okay, this is the general flow. Let us go over what we have here very quickly and see what you get. So the input circuit and the output circuit are low pass, and the pole frequency of a simple RC circuit is simply 1 over RC. So the answer to this is that it is 1 over RC. Okay, so what this means is that now for the two circuits that I have, okay, I have an input pole which is R sig prime times Cn, 1 over R sig prime times Cn, and the output I will have a pole which is 1 over L prime times C out. We agreed last time, because C is being multiplied by a gain, okay, we explained this last time, that if this is CGD times 101, that we might end up with 1 over R sig prime into Cn CGS plus 101 CGD، وهيدي حتكون البول اللي لها هي 1 over RL prime into maybe CGD times 1.01 plus CL. So which one we expect it to be the smaller frequency? Which one do we expect to be the smaller frequency? The input pole, because it has times 101. Right? So we expect this to be smaller than this one. So we expect this to allow me to estimate, if I assume that this is the dominant pole, then I can state that omega h is approximately 1 over R sig prime Cn. طيب وأنا I know that my low frequency gain هو minus GMRL prime. I can have an expression for my gain for my system. Okay, so this is R sig prime. Okay, so whole last time I'm just repeating them because we did not have a recording. From this we can find what omega h is, and we can approximate VO over V sig, and we can say that this is approximately the transfer function of my circuit. هلا if the gain is small, so they are of similar order, or for example, C load is large, okay, then I can calculate, will have two poles. Can I find the approximate 3 dB frequency for the system? If they are not, there is no dominant pole, I can use what method? I can use the better approximation method, for example. And so if the input pole is not much smaller, okay, then I can use the better approximation method. Because I only have poles, it will be 1 over square root of summation of 1 over omega pi squared, and like we see in here, and I still know what AM is, it's minus GMRL prime, so I can express it in a simplified form, the transfer function. Of course, I can still solve for the exact solution as well. يعني ارسم له البود plot للexact solution. Okay? طيب, anybody has any question on this slide? طيب, okay. So, هلا, what we have learned so far is that I can find the exact T of S بدون مطبق, without Miller. From it, I can know what the poles and the zeros are, and I can estimate omega h either by the dominant pole better approximation or the exact method. Okay. Then we learned about the Miller approximation method. We find the midband gain, so we find AM. We apply Miller. We get a simplified transfer function. Of course, the simplified transfer function will be the exact in this way. And I can find the poles and the zeros of the circuit. And either I I find omega h through the dominant pole, or the better approximation, or the exact method if I derive VO على VSIG, if I have all the transfer function. Now there is a method, okay, that does not require that I solve for T of S. There's a method that directly finds from a specific circuit, okay, the time constant and then the approximation for the 3 dB frequency. This method is called open circuit time constant method. And what this does is it handles things one at a time. So it handles one capacitor at a time. So it assumes that starting from the original circuit, I'm going to add one capacitor at a time and see what is the resistance that it sees. Let us see how this works. So for this method, if we want to put forth the rule, let me assume that I have a simple VSIG and a resistor R and a capacitor here. If we want to say what is, let us say that this is R sig and that this is VSig and this is C1. If we want to say what is the resistance seen by C1, okay, then in practice, what I am really doing, I am removing C1, right? So I am removing C1 here. I am putting a VXIX in its place. And I am saying what is the resistance seen in this way. So what do we do to the supplies? We make all the supplies shorted, right? So we set this to 0. So we're going to short the supply. And we're going to put in place of the capacitor a VXIX. Yeah, that's what we will do. And we will say find what Vx over Ix is. In this example, what is the resistance seen by C? يعني إذا رجعنا رسمنا, if we draw the circuit all over again, the circuit was like this, and I had C here. So if we want to say what is the resistance seen by C, it is R sig, right? The resistance seen by C is R sig, لأنه V sig gets shorted, and I put Vx and Ix. It's exactly like when you study R out and set Vn to what? To 0. Okay? So the difference here is that we set the signal voltage to 0. Now, if C1 sees R sig, this means that C1 contributes to a time constant tau 1, which is equal to R sig times C1. So we repeat the same for every capacitor in the circuit. So if I have capacitors Ci, we calculate tau I as Ri times Ci. And eventually the 3 dB frequency is going to be 1 over the summation of tau I for all the capacitors. Okay, this is the gist of the methodology. So let us follow the rules here and then I will open room for questions. So to determine the 3 dB frequency directly from the circuit, we approximate it as 1 over the summation of the different time constants. If I have 5 capacitors in the circuit, I will have 5 time constants. Ci, each Ci is a capacitor in the circuit. RIO is the resistance seen by that Ci, يعني the resistance seen when I apply Vx and Ix in place of the capacitor and when I set the signal voltage to 0. Okay, I remove all my signals, not Vn here. I remove Vsig, the main signal, I set it to zeros. With all the other capacitors, this is very important. with all the other capacitors open circuited. يعني I keep only capacitor I, the others I open circuit them. And the signal sources set to 0. So also the signal sources, I set them to 0. So tau I then becomes the RIO times CI. And this is why we call it open circuit time constant. طب هلا we're not going to have things be complex, and let me just share with you this. Let me share with you this sheet here. What happens here is that if you recall this resistor sheet, we can start to rely on these resistor rules. يعني the resistance seen by the capacitor. For example, I have a capacitor here. Okay, so I'm just giving you an example because you can reuse those capacitors. Let us assume that we have some signal here. Okay, and that this is grounded. And we want to find what is the time constant or what is the resistance seen by this capacitor. Okay, the rule says set Vsig to 0. Okay, so this will be shorted when I want to find what's the resistance seen by the capacitor. And then I will be looking into the drain of the transistor with a resistor RS. So once I can match this pattern, I am allowed to use this equation. Now we're going to show one example, not this circuit because this is too early for us to see now. But I'm just trying to tell you that what we will be doing is we will be taking those rules that we gather in this sheet and we will be using them for our benefit to try. Yes, Ryan, the sheet is on Moodle. We will be using this for our benefit so that we can use those rules that we gather as we move in the course. Okay, so let us go back to our example because this is a look ahead. Anybody has a question? Yes, please. Go ahead.
Yeah. That's when you said set the signal sources to 0. Could she DC or AC and we set them to 0, right?
Yes, when we are studying the small signal, we have already set the DC to 0. So in the small signal, in a similar fashion, if you recall when we used to study RO, we used to set Vn equal to 0. Okay. Okay. For the RIO of the capacitor, we will set V signals to 0. And DC already راحوا, they're already gone. Okay.
All right. Thanks.
Okay, thank you. Okay, so so then here, this is the rule for the that we just spoke about. Set the signal source to 0. All capacitors opened. RIO بنطلع time constant. It's a summation of the time constant. Great. So the frequency 1/2 pi times omega, right? So we divide by 1/2 pi. Okay, so let us come back now to this circuit that we have here. So for this circuit that we have here, how many capacitors do we have? We have 3 capacitors, right? And in those 3 capacitors, we have to handle them one at a time, right? So to handle them one at a time, let us start first by CGS. Okay, because it is the simplest capacitor. Okay, so if I want to start with CGS, what does the rule tell me? Open circuit all other capacitors. Okay, and set the signal to 0. Right, so I will end up with, so CGS. Okay, let us first agree. CGS exists here in the middle. Okay, from this side now I have an open circuit. In this place I have an open circuit and I have this. And then from this side I have the resistor and I have shorted my signal. One thing for us to be careful in this case it does not hold, is that the resistance that CGS sees is based on the current that is being sent from it. And if I replace it by a VXIX, so CGS is going to look into its IX and it will branch left and right. The right side is an open circuit, so there is nothing for it to see. This is why in this case we are only looking into the R sig prime side. So what is the resistance seen by CGS? So what is the resistance seen by CGS?
R sig prime.
R sig prime. So because this is an open circuit, in reality CGS is only going to look this way. I don't have anything and I will see R sig prime. So CGS and the time constant, CGS times R sig prime. And this is tau CGS. Okay, so this is easy. Okay, anybody has any question about this? Okay. Okay, great. So this is what we did. Now we're going to, okay, so here he's showing me the 3 capacitors. He's starting with this. He says this is the effective resistance and time constant. Now, the second circuit is for CGD. So if we want to look at the circuit for CGD, I'm going to go back to the previous slide and draw on top of it here. So I'm going to open this one. I'm going to open this one. I'm going to set Vsig equal to 0. So all of a sudden, I will end up with a, this is the capacitor that remains. So this is the only complex case that we will see. So this is between, if I want to put Vx instead of it. Okay, and this is the current Ix. Typically, the complex capacitors that you see are those that sit between the input and output. يعني CGD هي حيكون complex. The others that sit either only at the gate or only at the drain, they see simple conditioning. And we will look at the rules from the transistor perspective without flattening this way. So let me now just take the absolute circuit as is, and let us come up with a specific rule. So if we want to draw the rest of the circuit around it, C is an open circuit. I have here R sig prime. The voltage from here to ground is what? VGS, because this is node G. And then here I have the GM VGS. Okay, and then I have RL prime. Okay, so the effective resistance for this circuit is really Vx over Ix. Okay, that's the effective resistance that I'm going at. First, we will give you a hint how to derive it, and then show you an effective model that is available in the resistor sheet, which we can use from here on. So we don't have to derive it all the time. Let me ask you a question. If this node is at VGS, what is the value at this node? If this is VGS, what is the value here?
VGS plus Vx.
This is VGS plus Vx. Great. Yani now I can have KCL at G. So at node G, I know that VGS over R sig prime equals to minus Ix, right? Because this is the current that flows in it. So this is the first equation that I have. And then at this node, at node D or at node VO, I have Ix is equal to GM VGS, right? So this current is those two currents, plus VGS plus Vx over RL prime. This is equation number 2. What I can do, I can find a relation okay, between VGS and IX. So this is easy. So I can plug in VGS as function of IX and replace it here. Then I will find what is the relation between Vx and IX. Yani I am going to substitute here VGS is equal to minus R sig prime times IX, and then I can find the ratio of IX, Vx over IX. Okay, this is how we solve it if we were to proceed with it, and then I will find what RGD is equal to. Let us now start to make it look nicer. So, anybody first has any question about this derivation here? Okay, is it clear that we took two KCLs where we put CGD and okay, طيب. Let us now, I'm going to clear this and progress in the slides. So, if we look here at the CGD, we put the VXIX and we put the KCLs and we find the relation. This is the relation that we get. And let us draw the circuit in a nicer way. So I had the capacitor and the capacitor was sitting here, and then to its left I had some resistor which was R sig prime, right, which was between this voltage here, which is VGS, and then to its right I have GM VGS and I have another resistor RL prime. What do you notice about the current source and the voltage on the right and the voltage on the left? They are dependent. يعني إذا هاي VGS هذه هي GM VGS. Okay, so if we want to draw another drawing for the rule, the rule says that if I am trying to look at the resistance between two nodes where I have a voltage here Vx, okay, and a resistance Rx, and I have here a current source which is GM Vx, and I have a resistor Ry. This we are going to call Rxy. هيدي الرول حنسميها rule of Rxy. And for this rule of Rxy, the effective resistance seen here between those two nodes, the effective resistance seen between those two nodes is Rxy, and Rxy is going to be Rx plus Ry plus GM times Rx times Ry. Okay, يعني Rx plus Ry plus GM times their product. So the resistor seen between those two nodes, right? Because that's where I'm going to plug in my Vx and Ix. The resistance seen between those two nodes is going to be Rx. لأنه هيدا الفولتج هو ذاته Vx هون, right? Plus Ry plus GM times Rx Ry. Let's see, Rx plus Ry plus GM times Rx times Ry. And the reason I was able to establish it is if the current on the right hand side depends on the voltage on the left hand side, which holds here. Is this clear what the structure? We'll draw it more clearly on the next slide, but does anybody have any questions? Let's look at the next slide to show you what the rule is, and then I will show it to you in the PDF sheet. Okay, so let me erase this and let's move on to the next slide. So the next slide says that anytime I have a resistor Rx with voltage Vx, and on the other side I have a current source that depends on Vx, and in parallel with a resistor Ry, if I want to find the resistance between those two terminals, then the rule is Rxy, which is Rx plus Ry plus GM times Rx R1. Okay, so let us see where this rule holds in our resistor sheet. So in our resistor sheet, this rule holds in the beginnings, before we talk about the transistor. It's rule number 3, and it says if I'm trying to find the resistance between two nodes, yani if my VXIX happens to be plugged in here, then I'm going to see Rx plus Ry plus Gm times Rx R. Okay? So this is the resistance looking between two nodes, or if my capacitor basically is here and I'm trying to find its time constant. Is this clear that we can apply this rule for our reduced circuit for CGD? Anybody has any questions?
Good.
Okay, great, thank you. So, now we know how to find what the value of RGD is. What is left is CL. So for CL, we need to find RCL. We're going to open this. We're going to open this. We're going to set this to ground. So basically, I have RSig connected to ground. What is VGS? And then I have here a GM VGS, and I have RL prime, and I have C load. So we want to see what is the current that is going to flow from C load, or what is the effective resistance that it sees. We will look only in this direction. That's the only direction the current from it can flow, because VGS is 0, right? So GM VGS is 0, so this will be open. Okay, and therefore, what is the resistance seen by RCL?
RL prime.
RL prime. Okay, so that's a done deal. Okay, done. We are going now to clear this, and let us see what I have. All the 3 time constants now. Okay, so I can calculate my 3 dB frequency as 1 over the summation of the time constants. And here he's giving me a numerical answer where he plugged in already the value of the resistors. You can clearly see, because RXY here, RX plus RY plus GM RX RY, always GM times a resistor is a gain, so this is much larger, times a resistor, and therefore from this method we can find the time constant and we can find the frequency. Okay, and we can also know what makes my frequency smaller. يعني إذا أنا I want my 3 dB frequency to be a little bit large to have good bandwidth, I know that it is affected by RGD, so there's a trade-off here, and I know maybe I need to play with CGD or what constants I can vary for my design. Okay, so this is how we can find a good estimate of the 3 dB frequency. Okay, Hannah, I want to show you how we could have found this without really drawing. So let us see. So here they're just showing us the answer that once we obtain omega h, we know what is the low frequency gain, and we know what this is. Okay, and so this is the approximate expression. But let us just take a simple look how we can apply those resistor rules before we go into this example. So let me sketch here. Let me sketch here for you. Let us assume that we had the common source amplifier. Okay, and let us assume we had here the V bias. This was VDD, and here I had RSig plus or minus V sig. Okay, and this is a ground. So how would I find the time constant for this circuit? Okay, so the first thing is I want to plug in my capacitors. So first thing, I will assume that I'm working in the small signal analysis, right? So for the small signal analysis, this becomes already ground, and this becomes ground, okay? And let us say that I have VO here, and we will start, let us assume that given that we have a load capacitance, pardon me, sorry, that we have a load capacitance, okay, yalla, something new. Let me bus, okay, so let us assume that we have a load capacitance C load sitting here at the output, and that this is the only capacitor, and I am asking you about the 3 dB frequency. Okay, so how would you find the 3 dB frequency using OCTC? What are the steps? Step number 1, open circuit all other capacitors. This is the only capacitor that I have, right? Step number 2, keep my cap, 1, right? So 1 is keep my capacitor, which is C load. Step number 2, set the signals to 0, right? So this is set now, the signal is set to 0. صارت هيدي النود. What is the voltage at node G? What is the voltage at node G?
0.
0, because R6 has no current, right? So VG is 0. So step number 3, okay, step number 3, I'm going to say, well, this is my capacitor, and I want to see what resistance it sees. So if the capacitor sends a current, it has a chance to go in those 2 directions. So what is the resistance that this will see? إذا هيدا transistor Q2 هيدا transistor Q1.
R1 parallel to R02.
صح. So this will see RO1 parallel to RO2, because this is no signal لأنه هيدي 0, right? So V here, VG equals to 0, and this is 0 and 0 looking from the drain. This is 0 and 0 looking from, sorry, this is 0 and 0, pardon me, looking from the drain. Okay, so this is how we will handle this example. Now, let us assume now that we have another example, okay, where you see the same circuit. هيدا عملناها ground بالsmall signal, ground بالsmall signal, and we tell you that you only have a capacitor CGS at the input, okay, وعندي ال R sig وعندي ال V sig. Okay, and we try to tell you, tell me what is the resistance, what is the time constant, and what is the 3 dB frequency. What do you do? First, you set V sig to what? 0. Then you will say, well, if this capacitor is sending a current, it will flow in this direction and in this direction. What is the resistance seen by this capacitor?
بس ل R6 prime لأنه هونيك
It
ما
is
في current.
صح R sig prime parallel لأن ال R is infinity, so it is equal to R sig prime. So from now on, you can use the rules that we have studied from those amplifiers to apply directly without having to flatten the circuit. هلا طبعا the most difficult one is this one, because it's going to look up and down, and so it is an RXY from a transistor. So هيدي ال RL prime لإلها حتكون هي RO1 parallel ل RO2, هي ال RX, ال RY عفوا, وال RX هي من هي الجهة from this side. All the resistance it sees from this side. So this is a little bit more involved, but as you practice problems, it will become clearer. But what matters to me now is that you are comfortable at least with the basic rules, that sometimes you don't really have to flatten into the pi model. We can use the resistor sheet regulations and rules immediately. Okay, طيب great. Yeah. Okay, now we will move on if nobody has questions to the next slide. So on this slide, they are giving me a problem of a common source amplifier with a current mirror. They give me all the information for the K primes, W by L, VT, VA, and the I reference. And they asked me to find, and as well as the R sig and the capacitors, and they asked me to find the 3 dB frequency FH اللي هي omega H على 2 pi using the Miller approximation, the open circuit time constant, and the exact method using the transfer function. طيب للميلر approximation بدنا نطلع GMRL prime. نحن we solved for GMRL before for the same circuit. So let us see what they tell us here. So here they tell me that we have previously found GM and RL prime, which is R01 parallel to R02, from the fact that GM is to ID over VOV, and I know that the current is 100 microamps, the I in the previously. And now we're going to pick up from this, and we're going just to fill in the blanks for the different expressions that we derived before. So I'm not going to walk through the problem because we derived the expression before for the Miller. لقينا أنه Cn شو بتساوي, and we found that the input pole is Cn times R sig prime. And he's just trying to show me the approximations, how far the values will be from each of the method. And then he says the output pole in a similar fashion is CL plus CGD into 1 minus 1 over K. And this is the output pole. It is clear that this is smaller than this one by at least 4 folds, and therefore I can assume that if the input pole is dominant, this is my 3 dB frequency. And if I want to use the better approximation, I will end up with this estimate for the 3 dB frequency. Okay, so عندنا 6.89 or 6.79. Okay, so this is just plug and play. Anybody has a question? Okay, طيب. Great. بالتالي وحدة in the second one, he's going to use OCTC. So again, plug and play. R sig prime is the RGS. RGD, he calculates it from GMRL prime and RL prime. هيدي هي ذات RXY equation. And look how large the resistance comes out to be. RL prime معناه إياها R01 parallel to R02, we have it. So this is the time constant. And then the 3 dB frequency comes out to be 5.87 megahertz. So this is 5.87 as opposed to 6.89. The difference is that here the OCTC did not split the capacitor into two. It kept it in its place and it found the exact CGD, RGD for CGD. The exact method, for the exact method, if you recall, we wrote it in the form the transfer function, some function of the 0 over 1 plus AS plus BS squared. Okay, and we said from A and B we are going to find 1 over omega P1, right? لأنه اعتبرناها smaller, and then from B, which was the product of the two, we will find the 3 dB frequency. We had a complex closed form, the second pole frequency. We had a complex expression for them, and if we use this complex expression from A and B, derive 1 over omega P1, we will end up having FP1 and FP2. Look how large the second pole compared to the first pole is, and of course we have a 0 that is very, very far. If I compare those numbers, what this slide is telling me that the error in the Miller approximation is around 13%, and the error in the OCTC is around 1.51%. Okay, so it's showing me that the OCTC is closer in the solution to the exact solution. Of course, because we kept the capacitor in its place, so it did not adopt the Miller approximation. Okay? This is what this comparison is intended to show you. Anybody has any questions up to here? Type. Okay. So, are you comfortable with the OCTC? because it is very important.
Yes.
Okay, great. Thank you, Liana. Okay. طيب. So then let us now jump into this example. If you recall, we had the cascade circuit, pardon me, and in the cascade circuit we had 3 stages. This is the first one, this is the second one, and this is the third one. He's telling me that the low frequency gain per stage is minus 42. Okay, but he's also telling me that each stage has a 3 dB frequency, which is 6 megahertz. Okay, now we agreed last time that the gain is the product of all gains and that they are all not loading each other, so I can assume that all the stages have the same gain, which is going to be AM, which is minus 42, over 1 plus S over, so this is 6 megahertz. We're going to find omega h from it, which is 2 pi times F, and so this will be omega h, right? So the overall gain of the system is what? From V in to V out, it is the product of these terms. So really, it is this cubed, right? So it is really this function cubed. This is my overall gain. So how can I find what is the 3 dB frequency of this system? How can I find what is the 3 dB frequency of the system?
Maybe use the better approximation method.
Okay, so yes, that is one option. If we use the better approximation method, how many poles does it have?
3.
3. So هيكون عندي 1 over the square root of 1 over omega. هلا هون انتبهوا انه الاوميجا اتش اللي انا عم حطها هي للاولد سيستم، يعني خلينا نسميها اوميجا A واوميجا A. So 1 over omega A squared plus 1 over omega A squared plus 1 over omega A squared. Okay, so this is the better approximation. So the better approximation is really had a single system. 2 pi times 6 megahertz is the single stage 3 dB frequency. There's another method that I can also use. If I don't want to use the better approximation, what can I use? I definitely cannot use the dominant, right? So what can I use if I don't use the better approximation?
You can use the exact method, which is
The exact
easiest to apply here.
Okay, so let us test the exact method. So the exact method is going to state that my A of S for the system is equal to minus 42 over and minus 42. Okay, so A of S is minus 42 over 1 plus S over omega A, and this all cubed. Okay, so at omega H, right? What is the low frequency gain here? The system kilo, we set S to 0, right? So at omega H, magnitude of A of S is going to be equal to what? Over radical 2, right? يعني low frequency gain over radical 2, right? This is clear for all of you, right? يعني إذا أنا عندي ال A of S هي minus 42 على 1 plus S على omega A all cubed. And low frequency gain اتفقنا هو minus 42 cubed. and at omega h, type the magnitude of A of S is going to be equal to minus 42 cubed على root 2. And that the magnitude, if I want to write it, what is it equal to? It's really equal minus 42 cubed over what? Over the square root of 1 plus omega h over omega A all squared raised to what power? 3. Right? Is that correct? حدا عنده سؤال لا طلعت هيدا الإكسبريشن هيك؟ Okay. طيب, what can I do? The first thing I will get rid of this term. هيدا بطير. Okay. The second thing what I can do is I can square both sides. So I will get rid of the square root. Okay. And so I will end up having that 2 is equal to 1 plus omega h over omega A squared raised to the power 3. So بدي جيبها لهون بدي اخد cubic root of 2 equal 1 plus omega h over omega A all squared. Right? And now I can just do simple math and solve for omega h. Right? يعني بتصير cubic root of 2 minus 1 times كلها square rooted and then multiplied by omega A. Okay, so let us see how the slides solve this for us. So if we go to this slide, we will find that if this is my omega A, that my omega h will be function of it. Okay, and if I use the better approximation, this is the answer that I will get for the omega h. Okay, so this is the answer that I will get for the omega h. So it's slightly far from the exact method. طيب, anybody has any questions? Okay, طيب, we will catch up inshallah on Friday and I will send